modern quantum technologies. And we want to understand the effects of environment fundamentally. And after this understanding, we want to control and engineer environments for our purposes. So in addition to Koç University, I am working at TÜBİTAK Research Institute of Fundamental Sciences, and currently I am in my sabbatical year at Sabancı University. Okay, so in this opening picture, you have seen there is a jumping tennis ball. Okay, so it hits to some tennis racket repeatedly at some time intervals. So I want to start with a question that do you expect this tennis racket will eventually thermalize with this tennis ball? Say this tennis ball is just taken out of the fridge and it repeatedly hit to your tennis racket. Do you expect that this tennis racket will eventually equilibrate with the cold tennis ball and it will thermalize to some low temperatures? Well, I cannot see your faces or I cannot get replies, unfortunately. But I think most of you will say that this is not possible, yes? But why it is not possible? Well, first of all, you expect that after hitting the tennis racket, the state of the tennis ball will change. And if you cannot use a replica of the tennis ball, and if you keep using the same tennis ball repeatedly, make sequential collisions with the tennis racket, the state of the tennis ball will always change. Okay, so this is not something that we like in an environment. We want our environment to be robust. After interacting with a small system, the state of the environment should stay the same. Okay, so this is against our understanding of environment. So a single tennis ball, by repeated interactions, is incapable to homogenize the tennis racket with its own initial state. Okay, but what we could do is we could take hundreds or thousands or millions of tennis balls at the same cold temperatures and just hit them, the tennis racket with them. And eventually, in this case, you should expect that the tennis racket will be getting colder and colder and eventually reach to the same temperature with these tennis balls. Okay? So this is the basic idea of the environment concept. Well, of course, since we are physicists, and after this understanding, we want to make some quantitative predictions and modeling of this behavior. Okay, this is not easy. First of all, it is not easy because we know from physics that we usually like to have a single oscillator, a pendulum, a single particle, a small system to begin with. But this system, by its nature, it is already involves a lot of particles, actually infinitely many large degrees of freedom. So this is a headache for a theoretician, right? And also this is a time-dependent problem. So the initial state of the bath particles, environment particles, is very complicated. It is also need to be modeled. And also the state of the system can be very different. But what we know from this thermalization, that it will homogenize with the bath particles temperature. So therefore, the final state should be independent of the initial preparation of the system, right? So this is also making it a little bit difficult from theoretical point of view, and also it can take a lot of time. Yes, so the interactions can be strong. So you may not need to do perturbation theory. So many of our luxuries as a theoretician can be absent in this problem. Okay. Well, what a physicist should do in such a situation? Well, first of all, we take a model system. Okay. So one type of creature that enjoys thermal equilibrium is also very familiar with our physicists usually. It is a cat. Okay. So a cat is usually a large object, enjoys the sunshine here and also some sand, but it equilibrates with the air molecules. And there are a lot of air molecules messaging this cat and trying to bring it into some thermal equilibrium state. So how a physicist should model this problem? Well, first, we want to keep things as simple as possible, but not simpler, as a wise man said. So what we know from elementary physics is that collision physics is the first thing we learned in Newtonian physics is the first encounter with a many-body problem. It's a two-body problem. Even then we simplify it to single-body problem, but still it's a two-body problem. So let's imagine that these billions of collisions our cat is enjoying can be modeled by a two-particle collisions, like a Newtonian physics. And this will be our starting point. Well, this is our first simplification. We want to model these interactions of the cat with the air molecules as a two-body collision, but the cat has a certain shape, but we don't want to get this additional complication. So let's assume cat is a big ball. Then air molecules can be complicated. There is nitrogen, water, oxygen, etc. But let's assume that the internal structure of the molecules at that moment are not very interesting to us. So let's assume every different molecule is actually an identical set of particles or just simple balls. And they are much smaller in weight and also much smaller in size relative to the cat's mass and cat's size, or the cat's representative ball's size and mass. Okay, so then our problem reduces that a big ball of mass interacts with lots of many little tiny balls, but we want to model this one at a time, a two-body collision. Okay, so now the problem is now getting similar to what we are seeing in our textbooks. And this is what we get at the end of this initial setup of our problem. This blue ball is very massive, sits at the center. It can have also some velocity. It can move around. And there are other little balls hitting to it. But again, this looks a little bit complicated. Some particles are hitting the ball, some are hitting to each other. And this is in general an interacting environment, again, which makes the things very complicated. Okay. So in every physical model starting point, we then make some assumptions and set the rules. Okay. And first of all, this is, of course, our cat is a three-dimensional object. So these balls are also plotted here like three-dimensional objects, and the velocities can also three-dimensional. Well, this is already very difficult, even after all this spherical cat assumption. Well, what we can do to reduce the degrees of freedom in a large many-body problem, we can think that can we reduce the dimensions first? So we can imagine that if the cat is living in a cartoon, like in a famous Tom and Jerry movie, the two-dimensional Tom can also equilibrate with a two-dimensional artificial environment, right? So we can model this like a two-dimensional problem. Well, in 2D, two-body collisions are actually something we know very well. We have also seen them in some examples in Physics 101 textbooks, that it's a common billiard ball problem. Yes, so billiard ball is something that you can find pool tables in institutes, and people play it to get relaxed, and some can get very ambitious and get even awards. So like this Woojin Park here working at Samsung Electronics, he's actually a well-known nuclear physicist and also has some cups and awards in the pool game. So we know that if we think about it, billiard is something that we enjoy, but now we change the rules of the game. So instead of what here Woojin Park is enjoying, there is a big ball on the table, and this is just our cat, and we are hitting it with these particles. And one thing that I like in the billiard game, it is not very chaotic. So you hit the target object here, the big red ball, our cat, one at a time. So not all the balls are hitting to the red ball simultaneously. Always one ball is hitting to the red ball at a time, and sequentially the next ball or the next player hits the target. Okay? So this is already very simplified, but you may say that this doesn't look like realistic in a real thermalization problem. There are many balls or many air molecules hitting to the cat. Okay, you are right, but in physics we start from some simplified assumptions and see if this gives us some solid results at the beginning. Then we get more and more complicated situations. So then this seems to be a reasonable starting point. Okay, so you have to be here, of course, suspicious that I am telling you some subtle assumptions, and you may be reluctant to buy all these assumptions, and you want to see the whole set of rules. But actually, there are really many assumptions in this business, and let's say we don't have time to read all of them, but I'm going to say a few critical ones. First of all, I've already told you that in this game, there will be many little tiny air molecules represented by little balls, and the cat is represented by a big ball, and we define an environment. And here a subtle assumption is that all the molecules are represented by the same balls. That means that we ignore the internal structure and differences between different molecules. So this is our first homogeneous environment assumption. Then I already told you that I want to have one collision at a time instead of multiple collisions to keep the things manageable, because I want to microscopically divide my problem, make some surgery, microscopic surgery of multiple collisions by saying that I'm only looking at a two-body collision in a short time. Then here another big assumption is that after the collision, what happens to the air molecule, all these red balls? I'm going to assume that it is discarded. It has no chance to come back and hit to the blue ball again. It is lost. It is lost in the air, in the environment. Okay, this is again, you may object this, but then go ahead and do the calculation. It will be difficult. So this is what I can do. I will go with it. If it gives me some reasonable answer and it explains some experiment, that is good. If not, I have to then maybe agree with you and add some another complication to my model and allow the red ball come back and make another collision with the ball. Okay. Then another assumption, another set of rules that in my long list is that the red balls will not be able to hit themselves to each other. So even after a collision with a blue ball, there is no chance or negligible chance the red ball will find another red ball and make a collision with it. Okay. Again, this assumption is even more dangerous because there are already many air molecules around the cat, and it's very unrealistic to assume that after colliding with the cat, the air molecule will not interact with another air molecule. This is a little bit far-fetched, but okay, if you buy this, I will go and do calculations. But if you don't buy this, the talk is over. Yes, so let me continue from here. Okay, in the long run, again, you can add this assumption, break this rule, and you can get some interesting results. Okay, but let's see that what happens in this case later. Actually, I will break this rule in later stages. Okay, but these assumptions are well known. Okay, so in this contract, the rules of the game actually defines a well-known environment, which is known as Markovian environment. Because after all these assumptions, what happens is that if you don't let red balls communicate with each other or not gossiping with each other regarding the state of the blue ball, actually, they have no memory. They have no chance to chat and talk about the blue ball. So they have no idea about the state of the blue ball. The environment will not know anything about the blue ball. It will hit it and it will be discarded. All it is, little fingers, little balls will be discarded. So therefore, the environment has no understanding of the blue ball. It has no memory. It's suffering a lot of Alzheimer and amnesia. Okay, so it will forget about the target. So these are the simplest environments that we can define, Markovian or no memory environments. And we will continue from here. Well, so far we were thinking like a physicist, but there are also immortal great physicists. And they actually know how to do very good simplifications. And Lord Rayleigh is one of them. In 1891, he modeled exactly the same problem of thermalization using a simple billiard ball model, but he used not 2 dimensions even, just he went with the 1-dimensional model. Okay, so it's very accessible article, like 25 pages long, something like this, and there are a lot of text, very good explanations, even starting with the Newtonian physics, and step by step it builds kinetic theory of gases, repeats some well-known results from chemistry, etc., and brings many things all together very nicely. It's very good reading. So I suggest you to go ahead and read this. Nowadays, you know, the papers are much shorter, like even if you have 4 or 5 pages, this is usually good enough. But these long papers and very detailed, very explanatory, very pedagogical is rare gems, and I suggest that you should read this. Okay, so he has in this long paper, I will just look at these 3 equations. These 3 equations should be familiar to you. So these 3 equations are obtained after Newtonian description of a two-body collision and generalizing to many-body case by assuming that the collisions are very fast. One particle denoted by P, which is the big blue ball, is very massive relative to the small red ball. And under this fast collision and heavy or hierarchy of masses assumptions, you can do these calculations very easily. And if you look at the equation 14, this is just the distribution of the velocity of the particle P after the collision events. And it's a distribution because initial velocities are also assumed that they are given probabilistically or stochastically. Okay, so accordingly, the end velocities are also just probabilistically given as a distribution, and distribution has an exponential form. It is exponential of square of the final velocity multiplied by some coefficient. And if you go ahead to the Newtonian physics and two-body examination of this result, and you will get that this h is inversely proportional to the kinetic energy of the incoming projectile. But if there are many projectiles, then you can define a quantity known as temperature as the average of this kinetic energy, a mean kinetic energy. Then you can bring or replace this kinetic energy with the temperature concept. In this case, what you will get is known as Maxwell's velocity distribution. Okay, so starting with the Newtonian physics and doing some assumptions, realistic, reasonable assumptions, and going statistics by assuming the initial velocity distributions are given probabilistically, you end up with the famous result of kinetic theory of gases, Maxwell's velocity distribution, which is distribution of the particles' velocities when these particles are in thermal equilibrium with a hot environment at temperature T. So this is a powerful result showing the corresponding theory is still at work and can be useful. Very well. How to go to more modern questions? Of course, big masses making two-body collisions are nice, physics 101, and it shows the power of simple approaches, etc. But what happens if the particles have not this nice assumption that the projectiles have comparable masses with the target system P? So Q and P are comparable masses now. So immediately we lose some assumptions here. So in this picture here, the velocity of the projectile do not change much. And also you can make some approximations and expansions with respect to mass ratio and so on. So it helps us if you have some small parameter in your theory. If you don't have this, then you cannot go much with the analytical calculations, but still this model can be useful from numerical point of view. You can still use the two-body collision analysis when the masses are comparable. The analytics will be messy, but numerically it is still easy. So if you can write a computer program, assuming that there are projectiles prepared at the same initial state, and evolve the dynamics for some collision time at a given arrival time of the projectile onto the target, and just solve a simple two-body classical Lagrangian Hamiltonian type problem numerically, then repeat this process for every projectile. And then again, you can find the final long-time evolution classical state of your particle. So this is again numerically a reasonable strategy, but it requires a lot of numerical effort, and you have to buy a new computer and ask money to somebody. This is what we call as project funding in our business. So we have to justify, I want to do this calculation not only for my curiosity satisfaction, but it should help at the end to the general public. But really, how it helps. Well, we have to insist on our dreams, and we believe that if we can numerically solve this problem, it can still be useful for some application or for some fundamental improvement. Okay. So for this, let's take a limit. So here we said that, okay, let's assume that projectile and the target are comparable, are of comparable masses, but let's assume that the target is not only small mass, but let's take the limit. This mass goes to 0. Do we have an object that comes to mind with mass goes to 0? Well, if you are familiar with optics, our waves, our photons, our light is considered to be massless object. So now our problem changed a little bit. our projectiles are now hitting to some wave, like a light wave, a photon maybe. Then it tries to thermalize it. So photonics, we know there is a lot of money in photonics industry, so maybe this has some application there. Well, basically what we are trying to model is that we have a target, this red box here, in thermal equilibrium with the thermal environment. So our little projectiles hitting to the targets are modeled in this collision model by tiny particles. And in this box, there is an electromagnetic wave, and it will going to be thermalized with my thermal projectiles. And if I open a hole in this little red box, I can get out this radiation out. Well, this can be a hot oven. It can be used to, heat something. It's a chaotic thermal electromagnetic radiation. Heated waves will scatter after you open the hole. But this is, again, should be very familiar to you. I hope in Izmir you enjoy a lot of sunshine, but this is just actually modeling what the sun is doing currently, right? So maybe it is not that, from economical point of view, a big invention, okay? So actually, this is already very well known. This is just what we have just described, some macroscopical model, how we can generate a black body radiation, okay? Well, we cannot make much money from generating black body radiation. So we should continue to think in our idea, can it be more significant? Well, black body radiation is good for heating, but it is like many pedestrians chaotically moving all around, and they are not producing much work. If you want some power and work, it's better to make these pedestrians in a more organized fashion. So if they move in a phase, arranged wave, in a regular wave, all in the same phase, like a marching battalion or marching army, then this is a good representation of power, okay? So the upper picture shows a chaotic behavior. The lower picture shows a phase coherent behavior or simply coherence. So if you have coherent light or organized phase coherent waves, then they can be more powerful. And we know that in our modern society, from barcode readers to medical imaging, laser is already a coherent, organized light radiation, in contrast to black body radiation, and there is a big industry for it. So can we use collision model to produce a laser radiation? Well, we have already seen that if the projectiles are thermal, this cannot be done because the end result will be a black body radiation. So we have to engineer this environment. And immediately you realize now the power of the collision model, because it allows you to describe macroscopically how an environment should be, how two-body interaction of a macroscopical constraint of the bed with the target system can be. All are now controllable, and we can just be clever to put some proper stuff in this blue box, the target, and the gray environment instead of thermal particles, and hope that the result will be coherent. Well, now we go quantum. So let's look at, so far we have ignored the internal structure of the projectiles. We just said they are just thermal balls, thermalized balls with moving some velocity. But they also have, if they are very, very tiny, like atoms, they have, from quantum physics, they have some discrete energy levels. And if what we mean by a thermal atom or a thermal particle is that the population of these energy levels obey the Maxwell-Boltzmann distribution, which means that the lower energy levels are more populated than the excited energy levels. And our previous result, this black body radiation, says that if the ball is thermal or if the populations are distributed like a pyramidal fashion where excited states are at lower populations, then the result will be chaotic radiation. Now let's go to the opposite case. Let's assume that now the excited levels are more populated than the ground level. This is known as population inversion. So you can simply pump atoms to higher energy levels, excite them by giving some energy. You can do this part incoherently also. You can use some energy excitations to excite other energy levels, and then you create this population inversion. What happens if I put all these projectiles sequentially interacting with my target in a non-thermal population inverted state? Well, it is known that if you can engineer such an environment of projectile or atoms or particles in population inverted states, the end result will be not chaotic. The end result will be that radiation will be coherent. All the waves escaping from the little hole that we will punch in this box, it will emit some radiation, a wave, but the next wave, all the other waves will be in phase, and therefore it will produce a lot of power relative to incoherent emission. Okay. So how do we know this work? Of course, people has to go through the theory of this radiation emission from population inverted atoms. So basically, you have to understand how atoms in quantum mechanical sense emit radiation. Okay, and this is a fundamental question solved in a field of physics known as quantum optics. And one of the prototype experiments actually in quantum physics is known as micromaser. Okay, so once we understand that we have this hypothesis that population inverted photons, they may emit coherent light. If they created like a beam of population inverted atoms sent into some optical cavity, they will emit coherent light. And people did experiments by exactly building this idea. They produced atoms in population inverted states, and they sent these atoms one by one through between two mirrors, which is trapping the light. And from these mirrors, you don't have to punch a light, punch a hole on these mirrors. It will just emit and leak some radiation, but this radiation now will be coherent. Okay, this is known as micromaser. And of course, I am telling you this not from my gut feeling, but people really studied this hypothesis and they did a lot of theoretical calculations and experimentally verified. And one of the leading papers in this, written by Marlon Scully and Wills Lamp many years ago, late 60s. And as you can see, one picture, figure 2 of this paper, exactly shows the difference between blackbody distribution of photons. So in the photons, as a gas, if they are like a blackbody radiation, as you can see, the average of photons is 0, but if they are coherent, there is a non-zero average of photons. And you get a powerful coherent emission from the micromaser. And since quantum optics is by definition quantum statistics of light interacting with matter, this is one of the seminal papers in the theory of the quantum optics, and also it is experimentally verified that we can get coherent emission using this application of collision model. And then such devices, of course, used to check the many predictions of quantum optics as the first quantum revolution, and it led to development of laser and maser applications from medicine to commercial applications. But what is important for us is that the state of the particle or the distribution of photons is very different than blackbody distribution of the photons. It is a different Poissonian type distribution. And therefore, you can say that you are engineering quantum states in micromasers. And therefore, this is one of the first examples that is also important for second quantum revolution, is that we can use collision model for quantum state preparation. And the more modern application is that since the atoms are coming in inverted states, you can imagine this is like a battery, because you are storing some energy in excited states of the atom, and then you transfer this energy to optical field. And this process can be modeled like charging and discharging of a battery, and you can make some quantum batteries. And one of the modern application of this collision model is to use micromasers as efficient quantum batteries. Well, this is all good, but first quantum revolution has its limits nowadays, and we go to more modern second quantum revolution. What is the difference between the first and the second quantum revolution is that we have now a single quanta control ranging from photons to atoms, even to molecules and so on. So we can control single quanta, and then we can also put this quanta in so-called superposition or non-local states and exploit some quantum advantage by harnessing these quantum superpositions. One of the big important superposition, may be familiar, of course, to all of you, is quantum entanglement. is that now can we do micromasers and modernize them to next generation micromasers and next generation collision models for second quantum revolution. Well, the second quantum revolution, as I said, enjoys superposition, and superposition is a concept coming from wave-like physics. So in quantum physics, we know that if you just make the size of the container of a particle and shrink it down to comparable to de Broglie wavelengths, then you get to see some wave-like behavior of particles, and this is known as wave-particle duality. And this is at the heart of the second quantum revolution. We want to understand how these wave-like properties can be harnessed in the case of non-local advantages. And one of the early works that has been done in this modernization of micromasers to second quantum revolution comes from our group in collaboration with Gershon Kurisky group and Ceren also. One of our students contributed a lot to these applications. So as you can see, what is now used in micromaser pump beam or collisions, the electromagnetic wave trapped between two Fabry-Perot mirrors are no longer interacting with a single atom, but two atoms. And these two atoms can be put in entangled states. And then if you study the quantum state or emission out of one of the mirrors, is no longer thermal, no longer coherent, but in some more profound, more deeper non-local quantum states like quantum squeeze states or thermal coherent squeeze states. So you can engineer different quantum states relevant to more modern applications of second quantum revolution by this way. Well, this was an application, but more recently we look at more fundamentally and revisited this Lord-Rayleigh's problem and look at this problem more fundamentally. These two atoms, when they are prepared in entangled states or coherent superposition states, are now, as Onur nicely plotted here in figure B, are in some like wave-like states. And we want to study how their quantum wave-like properties influences the quantum state of the cavity. Okay, so the cavity here the plot shows it like a microwave oven actually. So in our microwave oven, we are now using entangled particles. And what happens, interestingly, what Onur and myself we have argued and showed here is that in addition to energy in the form of heat exchange between the cavity light and the atoms, there is also information exchange between the bath and the system. Okay, and moreover, this information and the heat can be exchanged to each other. Okay, so you can convert this entanglement or superpositions to heat, and heat can also be in return can be used to generate entanglement, and this is actually very interesting. So we built upon these ideas and studied if collision model, even without a cavity, by just collisions, can you scalable large entangled states. So this is in collaboration with Mauro and Steve and Bassano and also Barış Çakmak and myself. We showed here is that by clever design of the collision protocols, you can generate multipartite or large-scale entangled qubits or entangled particles, which are very important resource because we know that quantum advantage scales with the size of entanglement. And with these collisions, you can sustain them over long durations. Then we also studied if, in addition to entangled state generation, one of the bottlenecks is in quantum technologies is that you need to rapidly cool them to reset back them their initial states. And for this resetting problem, you need you are limited by the thermalization time, and you know if you cook something or if you put something in your fridge, it takes a lot of time to cook or cool down something. But if you can again engineer the environment by collisions and do microscopic surgery, how rapidly you should collide, how this interaction should be, and what should be the initial state of the particles. And also if you make multiple collisions now simultaneously, one of the assumptions that we break now, we can see that you can get super thermalization effects. A super fast thermalization can be achieved. And we have found there is a nice Young tables and other deep fundamental symmetries. That is why it should happen. So there is also some theoretical discussion. If you like the math, you can also read these papers. But I'm just giving here the basic message of the result. Then so far, the targets are very simple, like a single qubit, a single cavity field, and so on. But of course, in real life and modern quantum technologies, the target systems can also consist of like an Ising chain, like a quantum annealer or something, some spin chain. If you want to look at the thermalization problem of spin chains, then quantum integrability and thermalization is not very well understood and solved problem. But the collision model illuminates this problem also. You can design some schemes how to thermalize or maybe not thermalize different quantum networks by making multiple collisions with the qubits or the nodes of this network. So we studied and developed general conditions under which a quantum network can be, a spin chain can be thermalized and brought to some desired states. How to do this? Then as an application of this idea, we have shown that an Ising model, transverse or longitudinal, can be brought to low temperatures by a few qubit collisions only. And one of the practical limitations of quantum technologies, they are very large. You need large dilution fridges to realize them. But if you have compact qubit refrigerators, or if you use one part of quantum network to cool the other part of the quantum network, then this will be more compact solution to cooling and resetting type of problems. So this is the objective and application of this fundamental result to cooling down a quantum network with few qubits. And this is one work that we have done with my student Ali and also Barış. And here we studied, can we understand or use these collision models to simulate complex systems. So quantum simulation for drug design, for biology, medical applications in quantum technology is very important and attractive, but they usually require some molecular structures, multiple environments, and so on. So here we have a three-environment system and hierarchically coupled to a molecule in the middle. And they described some heat flow from hot to cold bath in the presence of some background matrix molecule. And this background matrix molecule can feed information and heat into the system as well. So it's a complex environmental model. And in biological and medical systems, the couplings are so strong that you cannot do perturbation or open system master equation methods. But collision model is free from perturbative approaches. You can exactly study two-body interactions and make realistic quantum simulations. Then we break another assumption in this paper that now the bad particles can interact with each other. In this case, you have no longer Markovian memory, memoryless environments, but now the environment has some information storage capacity and it has memory. And modeling them requires some integral differential equation solving in master equation, also perturbative. But collision model allows to do this without this integral differential equation solutions. Just step by step, you two-body interactions solved exactly using numerical methods, and then you can propagate this system and get interesting results. And of course, one critical point in any quantum technology is the coherence. Currently, all quantum computer developers are trying to solve this problem, or either by fault-tolerant error correction methods, or by improving their systems and so on to maybe parallel modular quantum processing solutions, etc. So quantum decoherence is a bottleneck. But how to understand it and collision model can help it or not is really a positive answer can be found here, because collision model allows us microscopic understanding of environment. Then we can also define the coherence using collision model. So one relevant concept is coming from quantum Darwinism approach to quantum decoherence. The basic idea of this quantum Darwinism is that it's the survival of the fittest. So there are some pointer states showing the eigenstates of a observable a measurement apparatus. And it can be in some superposition state and so on. So there are many pointer states, but some pointer states are what we observe in our classical world, or at the end of some evolution at the classical level, we lose quantumness initially. So initial quantumness change to classical behavior. This quantum to classical transition is something that all observers like us in classical world agree when we make observations. So survival of these fittest pointer states needs to be understood, and we did some work with Barış, Mauro, Basson, and Steve that using the mutual information concept, we can see some plateaus as the number of observations increases, agrees with the Darwinism expectations, but there are some differences and loss of plateaus. If there is quantum coherence in the system, it has to be eliminated eventually also.
Sayın Hocam, çok özür diliyorum. Bölüyorum ama son 5 dakikamız konuşmamız için.
Teşekkür ederim. Zaten bitmek üzere. Okay, so I told you that collision model can be numerically programmed and allows you to study some regimes inaccessible to analytical methods like strong coupling, non-Markovianity, interacting projectiles, and so on. And to code it, you should understand this like a Turing machine, a fundamental Turing machine. So the target we want to investigate is our Turing machine is moving on a tape, and this tape can be envisioned like projectiles. And these projectiles can be encoded into some different quantum states. Okay, so once you understand this, you can see that collision model can be implemented in any classical quantum or any type of quantum or computational machine easily. So in the language of modern quantum computers, we use so-called like a composition of a music sheet. We have quantum circuits. So this at the bottom you see rho 0, eta 1, eta 2. These are some quantum states. Eta 1 and eta 2 are projectile states. Rho 0 is the target state or Turing machine state. Then two-body interactions are represented by propagators U1 and U2. So if you know the module of Hamiltonian of interaction and its duration, you can easily calculate them. And then you repeat this sequentially over many steps. So this is how you write a quantum circuit to encode a collision model onto a quantum computer. That, as I said, we used collision model also to simulate some proteins, molecular systems for drug design and so on. So these are also usually can be easily implemented on quantum computers. And if the system is more complicated, more interacting, you can also design your circuit more complicated. These are all done so far for Markovian channels. But if there are also non-Markovian channels, then you just need to add the interactions between the projectile qubits. And this is also studied, and now we have a general understanding that collision model is actually so powerful that any arbitrary quantum channel, either Markovian or non-Markovian, can be easily programmed onto quantum computers. Then ranging from quantum simulation to quantum gate designs, it has a lot of potential as shown in very recently in some works. Okay, so I conclude that the collision model is actually, even from early 1800s, is known as oldest descriptions to understand microscopically how environments act on thermalizations, but modern perspectives are using them to engineer and make a surgery of environments on purpose for quantum state generation, for quantum simulation, and to design new quantum technologies ranging from batteries to quantum thermal annealers. Okay? So thank you very much for your time. If you have any questions, I will be here.
Sayın Hocam, değerli katılımcılarımız, teknik bir aksaklıktan ötürü soru cevaptan önce sizden bir dakika rica ediyoruz. Anlayışınız için teşekkürler. Hocam şu an konuşabiliyor musunuz?
Evet, duyuyorum ben sizi.
Hocam. Evet hocam. Şu an sorularınızı varsa alabiliriz.
Soru varsa siz bana getirseniz benim buradan duyamam herhalde.
Teşekkürler bu konuşmanız için. Benim merak ettiğim bu non-Markov olmayan environment'larda duran yön hareketi geçerli değil herhalde, değil mi? Level flight geçerli ve burada Boltzmann istatistikleri de geçerli değil. Öyle mi?
Evet, termal olmayan Markov olmayan çevrelerde biz evet o assumption'ları yapmıyoruz. Zaten collision modelin güzelliği, çalışma modelinin güzelliği orada. Yani standart bütün bu kabullenmeleri kırabiliyorsunuz. Farklı termal olmayan bir kuantum durumla projektayları çarpışan parçaları hazırlıyorsunuz. Sonra aradaki etkileşimi istediğiniz gibi yine tanımlayabilirsiniz. İsterseniz two body, standart klasik ya da kuantum Hamiltonian'larla. Arkasından bunu belli bir zaman içerisinde evolve edebiliyorsunuz. Bunu bir uniter bir evolution yapıyorsunuz. Eğer non-Markov'sa o zaman onu non-uniter ya da farklı şekillerde modellemek mümkün olabiliyor kanalları.
Peki bu non-Markov environment'a ilişkin nasıl equation'ları fractional dinamiklerle ifade ediyor?
Non-Markov'da orada onun o hafızanın ne kadar derin olduğunu tanımlamak önemli oluyor. Orada sistemle etkileştikten sonra projectile, kübit, başka bir kübite o bilgiyi aktarıyor. Onunla etkileştiriyorsunuz. Yani artık sistemle etkileştirmiyorsunuz. Çevre içerisindeki başka bir kübitle etkileştiriyorsunuz. Sistemden öğrendiği bilgiyi başka bir kübite aktardıktan sonra ona discard ediyorsunuz. Sonra bir sonraki kübit sistemle etkileşirken o aldığı bilgiyi sisteme geri verebiliyor. Böylece bir information feedback loop kuruyorsunuz sistem üzerinde. Eğer birden fazla kübitle etkileşirse discard edeceğiniz projectile bu durumda depth of memory artabiliyor. Yani değişik memory kernel'ları tanımlayabiliyorsunuz. Açık sistemlerde bunlar memory integral'lar üzerinde kernel'larla falan geliyor ama collision model'da çok doğal bir şekilde ve nümerik biraz işlemlerle yapılabilen şeyler olduğu için bundan Markovian kanalları modellemede ve kurmada avantajlı oluyor.
Teşekkür ederim.
Hocam online'dan bir sorumuz var. Ben ileteceğim size. Collision modellerinin bulunduğu sonuçları şu ana kadar destekleyen deneysel çalışmalar var mıdır hocam?
Tabii yani ilk deney zaten 1960'larda yapılıyor. Macro Maser, ilk collision model. Yani birinci kuantum devrimindekilerin hemen hemen bütün sonuçları zaten collision modelin gösterilmiş durumda. İkinci kuantum devriminde kuantum dağınıklık üzerinde de kuantum bilgisayarlarda simülasyonlar yapılmış durumda ve bu kuantum pil üzerinde de deneyler yapılıyor. Değişik uygulamalar açısından.
Tamamdır. Sayın Profesör Doktor Özgür Müstercaplıoğlu'na konuşması için teşekkür ediyoruz.
Ben teşekkür ederim. İyi toplantılar. Sağlıcakla kalın.